AI, AI and cryptanalysis. In recent years, AI techniques have entered like a storm in the world of cryptography. We can see that in forums like chess, one of the most important forums for applied cryptography, every year they receive an ever-growing number of submissions on machine learning-assisted side-channel attacks against cryptography. In this table, we will try to summarize some of the most important challenges and problems in this exciting new area where crypto meets AI. And we have an amazing lineup for this table, so I would encourage you to ask questions anytime. We will try to follow one structure. We will first ask each panelist to introduce themselves in a short way. Then I have prepared some customized questions for each one of them. After that, we will have some general fundamental questions of this table's topic. And finally, we will try to conclude if time permits. But again, if you have questions, please, by all means, ask the questions, because really it's a privilege to have this table that besides the high technical level of all of our panelists, as you can see, we have an excellent gender balance. And I am sure that Professor Christine here, she will be happy, and also Fatemi, and everybody, to be honest. So let's start. So who wants to start introducing themselves? Maybe we can start with Stefan again, please.
Yeah, so I already introduced myself, Stefan. For this session panel, I do quite a lot of work on AI-assisted side channel attacks, fault injection attacks, a bit on neural distinguishers. So let's say that's the more important.
Thank you.
Yes, my name is Aaron Gore. My research interests are mostly centered around using AI for cryptanalysis, but also side channel analysis.
Thank you, Aaron. Welcome here.
Hello, everyone. My name is Fateme Sabaganji. I'm an assistant professor at the WPI. This is Worcester Polytechnic Institute in the US. And I have been experienced working on different flavors of AI and machine learning, background of theoretical machine learning, and finally, I ended up using AI-assisted side channel analysis, where we can see how two different topics are coming together that are meant to be together, cryptography and machine learning.
Thank you.
Hi, I'm Kristen Lauder. I'm at Meta. So I'm director of FAIR Labs North America. FAIR is fundamental AI research, used to be Facebook AI research. So I went to FAIR about 2.5 years ago after being at Microsoft Research for most of my career for 22 years, leading cryptography and privacy research there. And when I went to FAIR, I was able to form new collaborations with all kinds of awesome AI researchers. I'd been working on private AI for about 10 years, where I call private AI is like using cryptography for AI, meaning trying to use cryptography tools like homomorphic encryption to protect privacy when in the whole AI pipeline, including training and inference. So I switched over from doing what I called crypto for AI. And when I went to Meta, I switched to doing AI for crypto.
Wow.
So meaning that in our recent projects, we are training AI models, machine learning models, to attack crypto systems. So in particular, post-quantum crypto systems based on lattices. I'm actually talking about it tomorrow in a couple of the workshops. So that's my main focus, is AI for crypto in that sense now.
Thank you very much, Christine. So Melissa, no, she's not here. Okay, so let's see if Melissa can join us later. So we will start with some specific questions for each one of our panelists, and I would like to start with Fateme. So in your opinion, Fateme, what obstacles researchers may face when working on the interaction between AI and cryptanalysis? What would be your thoughts about it?
I think this is a very important question to answer. As a young researcher, when I started doing these type of attacks, I was looking for different data sets, looking for different trained model, even a standardized method for collecting traces. And I ended up having only a few of them available. And I have seen some new initiatives at different conferences. For instance, at CHES, now we have the artifact chair, collecting the artifacts, trying to make it publicly available. Sometimes we think that our model is our proprietary method, and we want to force, if it is trained for, I don't know, government or very specific organization, it's fair to assume that we should keep it for us. But if we can share, we can learn from one another. I think having an open source ecosystem would be very beneficial to this community. And on top of that, what we have observed during the process of defining the last, let's say, the last remaining lightweight cryptography that NIST was interested in, we have observed that many different groups are doing different methods for assessing how well a primitive is designed, and the method for collecting even traces is not common. Therefore, one primitive assumed to be secure in one lab goes to another lab, and it will be broken with a few number of traces. I think it's time to have one, at least, initiative to think about ecosystem, open source ecosystem.
Thank you, Fateme. I don't know if anyone wants to add something more of what Fateme just said. Aaron, maybe? Do you want to add any further remark?
Yeah, I think, I mean, it's certainly true that standardization is an important thing. I mean, it would be nice to have everybody use sort of the same logical interface to building, let's say, side channel case, because even when people are submitting artifacts to a conference like CHES, then the artifacts normally they only cover. I mean, you have a set. Let's say you have a side channel attack. You have a set of measurements, and these measurements, and then you have maybe a model trained on these measurements, and this model will then successfully extract the key. But that doesn't define the whole experiment. It doesn't define exactly what you did to obtain those measurements, and it doesn't say exactly why you took exactly those measurements and not some other ones. And I think those bits, they are of course defined in the paper normally, but they are defined in natural language and normally with some ambiguities. And so I think it would be very good if one had something like an artifact for that kind of information too, sort of like a sort of program that defines what measurements you took relative to a specified logical interface.
Thank you. Yeah, I think it's not a coincidence that in this panel we have so many people from the chess community. And Stefan, you were saying in the last table that it is so difficult to see what is important with so many papers coming like always. So wouldn't you guys think that chess could make a difference in that sense? Because in chess, normally they ask for this source code for the implementations and things like that. Is it a dream, or is it feasible in the short term?
I'm not sure I don't think it's mandatory to have.
No, it's not, but it's
Yeah, yeah,
encouraged. Yeah.
It's recommended, but yeah, I would say still it's more on a level of a dream because people do submit code, but also then you need time from people who would really check the code, that the code really works as it should be, and then that everything is aligned, that different teams have different, of course, versions and whatever. So having something that's very nicely uniform across everything, I think it's still more on a level of a dream, to be honest. But definitely, side channel does seem to be quite active domain with AI, with machine learning. And while the number of papers is not significant compared to backdoor attacks or whatever, there is quite a lot of work. And I do feel it's already very difficult to recognize what techniques to use and what not to use. It's just enough to check the papers and say, well, this paper used this technique, and says, well, this is the way how to go. Check other 10 papers, none of those papers will use that technique. Why not if the technique is good? So we are really missing even the steps, what should a good attack have?
Thank you very much. Fair enough. Now I would like to switch a bit the topic towards how machine learning side channel attacks can be used for post-quantum schemes. And in this case, I would like to ask the question to Christine. I know that you have all these really hot papers, salsa verde, salsa, picante. Can you please elaborate a bit more why machine learners are so successful attacking, for instance, LWE schemes?
Yes, thank you. So actually, it was quite a few years ago, working on homomorphic encryption and working on LWE, that I noticed a really surprising aspect of the both LWE and also just the community, which is that in cryptography, LWE, learning with errors, is assuming that you're given a lot of noisy data, and it's assuming that you can't learn from it. So just think about that statement, right? In the context of AI. So what is the noisy data? So there's a dimension that's fixed of the vector, like n equals, let's say, 256 or 1024. And then there is a modulus q. So all the operations are done mod q. It's not like real or complex operations, it's mod q. And then you have a secret vector where the entries are mod q, but there could be different distributions. For example, there's binary secrets, ternary secrets, small secrets, random secrets. There's all different assumptions about what secret distribution you use. And then the LWE problem is just take a random vector, A, take the inner product with S, the secret vector, add some small noise. The noise comes from like a small Gaussian. And then give everybody lots and lots of pairs, A, comma, and then this noisy inner product. And then say, can you find S? So that's the learning with errors problem. And if you look in machine learning, we look at that problem and we think, yeah, we can learn from a bunch of, noisy data. And the only real difference is that all the operations are done mod Q. So if you were in the machine learning setting, normally you wouldn't be doing things mod Q. So for a long time, I really wanted to work on this problem. How come we can't just use AI or machine learning algorithms to try to find the secret? And so indeed, when I went to Meta, I built a team to start working on this, just a couple of interns to start with, but we had a paper in NeurIPS last year, which showed that yes, it's called SALSA. We can actually recover secrets from given a lot of samples. So I'll go into more details tomorrow, but we've been able to show different secret distributions that we can attack, primarily sparse secrets for right now. But, you just look at what AI can do. AI can, generate code on the fly that you can compile. I mean, it can do so many amazing things. So we just thought, why can't it learn secrets? And it actually can. So it's kind of cool. There are limitations to it. But the interesting thing is that in terms of the field of understanding AI or ML, The models that we train are so different from large language models. Large language models, they're just benefiting from, more scale, more data, more train, more attributes, features, whatever, all of that. And that just does not seem to be the case yet in AI for math and AI for crypto. So if you look at the models that we train, they're tiny compared to large language models. The good thing about that is that we have a better chance of understanding better, I think, what they're doing. But to be honest, so far, we don't actually understand them. We just use transformers and throw them at these problems, and they just learn, which is super cool, but lots of work to be done to understand them.
Thank you, Christine. I don't know if someone wants to add something here. Go.
Yeah, I'd like to add, yes, I mean, in symmetric cryptanalysis using AI, one sees sort of the same phenomena that small models work quite well. That small models work quite well, and that scaling the models doesn't necessarily improve them. Sometimes it makes the model even perform worse. And I think in symmetric cryptography that can be attributed to a sort of basically to a trade-off between the model size and I think sort of what one sees there is that smaller models, when everything is, as long as everything is equal, as long as the model can represent the function that you want to approximate at all, because maybe a smaller model means a smaller function family from which you are choosing, and this smaller function family might of course not contain the function that is in the end of interest to you. But if it can, if the smaller model is still capable of learning what you want to learn, then I think it can learn smaller biases. Because the bigger model has more parameters, and so has a larger capacity to do things like memorize the training set or to learn fictitious patterns. And and I think in symmetric cryptography we often have to exploit small biases, and I think it's a very interesting problem to get the best of both worlds. So to get models that can, on the one hand, represent complex functions, and on the other hand, also learn very small biases.
Yes, please, Fatima.
I think it's a very relevant point, as also mentioned by Stefan in the previous panel. Our understanding from cryptographic approaches is well, maybe understand it quite well. But when it comes to AI and machine learning, sometimes I can see that some basics have been overlooked. It is getting better. For instance, when Aaron mentioned that if the model has enough capacity, it can learn without memorizing the data. It is a procedure defined in AI how to understand if it has enough capacity or not. So just evaluate it, try to draw the learning curves, and we'll understand if it is overfitting or not. So these type of procedures should be provided to us cryptographers to understand, okay, what's the next step? Just having the model ready and apply the examples, the samples to the model could not be enough. We should really understand if it is not memorizing, if the capacity is enough, and perhaps it's time to think about the next steps of understanding why machine learning could be that beneficial. For instance, the approaches taken by Stefan into account when he begin from very large network, try to cut here and there nodes and layers and everything, and understand why the model has learned well, if that layer was necessary or not. These type of approaches. Or another approach that we have taken into account, start from very small network and let it grow by itself in the sense of neuroevolution, and see what these models learn. Is it possible to stop it at the right time with the right knowledge without memorizing the training data set, there are many different aspects of this problem to be considered by our community. And I believe this needs a good connection between two communities, AI and cryptography.
Thank you, Fatima. Any questions I think the debate is really nice, really shedding light on this topic. I have a question for Stefan. While you think about your questions, please interrupt me if you have questions. But I have a question for Stefan related to what Fatima was just saying. And maybe people here are curious about that also. So we are talking about the intersection of two areas, cryptography and AI. What do you think, Stefan, that is happening right now? Is cryptographers that are acquiring this AI tool to work with their problems? Or also AI people who are saying, okay, let's apply our knowledge, our expertise to this application that is called cryptography. Because it's a different thing, right? Like the difference between latte, cafe latte and cappuccino. No? Latte is milk with coffee and cappuccino is coffee with milk. And there is a difference. So what would be your thoughts about it?
Yeah, that's a good question. I feel it's still mostly crypto people going for various AI tools, which can be nice, but of course, then you always get a problem, you don't necessarily understand all the details about the tool, but you still say, well, I know enough to use it. And then, yeah, maybe you are lucky and use it correctly. Maybe you're a bit less lucky, but still it works. And then you think you are on the verge of something while you're actually going in the wrong direction. So I do feel it's mostly still crypto people going for AI. I do know there is also, of course, opposite direction, but then, yeah, then it's again a big problem because then it's AI people where they don't really care about crypto perspective beyond saying it's an interesting benchmark problem. And then you get into problems because then they use instances of problems that are completely irrelevant from the cryptographic perspective, like extremely short keys, that in practice would make no sense, but they say, oh, look, we broke 8-bit key or something like that. And so the learning curve, I think it's quite similar at the beginning from both sides. The bigger problem for us as crypto people is that there is many more people doing AI than crypto, which basically means there are many more things that you could potentially wanna or need to use.
Okay. Probably Christine wants to say something.
Yeah, I think that's a very good point, and I agree with you. But there are some exceptions. So actually, one of the things that I did when I went to FAIR is I built up an AI privacy team. So that's led by Kamaluka Charduri, who's a professor at UCSD, who is an ML researcher. And people in that team, like Chuan Guo and others, are really, they do have that AI expertise. So that's great. And what you see, though, is look at the problems they work on. They're not really the crypto problems. So, for example, relevant to the last panel, I really enjoyed the discussion in the last panel, but like memorization attacks, like being able to quantify to what extent models that have been trained can regurgitate content that they were trained on. Those quantifying like time and amount of harm that can be done, in those settings are more like the privacy attacks that they're doing rather than really crypto. The exception where I would look at the intersection is they do a lot of work on differential privacy. So if you think differential privacy is part of the crypto community, then that's definitely in the intersection. So trying to train, differentially private models. And so this whole field of PPML, actually one of the workshops tomorrow is PPML. And I've noticed PPML workshops at both crypto and AI conferences, but they have a distinctly different flavor. Like, so the PPML, privacy preserving machine learning at a crypto workshop will be mostly the crypto people, whereas at the AI workshops, it'll be mostly AI people.
Thank you, Kristen. And I don't know if you can comment on about your team. They are cryptographers that are work, like getting the AI knowledge, or the other way around, or combination.
No, in the case of Kamalika's AI privacy team, it really is machine learning researchers that are trained on the machine learning side, which is good.
Okay. Okay. Any other comment?
I mean,
Yes, please.
one area where there is some convergence, I think, is also explainability, because I mean, for instance, I think models, I mean, there's a natural interest by the side channel and also by the cryptanalysis community in explainability of models. And on the other hand, I think these models, because they are small and because they solve problems that are very, very well defined. And sometimes they solve problems that are also surprising, I think, in terms of what the machine learning community would expect. For instance, I think the machine learning community wouldn't have, or it doesn't seem like a natural application of neural networks to try to break a block cipher, because breaking a block cipher is basically, you can formulate it as a problem of solving a large system of equations over F2, basically. And or solving a large instance of satisfiability problem with a very special structure. And it's not a priori clear at all that you can do that efficiently with neural networks, but if with the right amount of cryptographic domain knowledge that you put into building a key recovery attack, and the right amount of domain knowledge into asking the right question, so into trying to build a problem that neural distinguisher, for instance, has a chance to solve at all, you can get it to work. And I think explaining how this works is interesting, or could be interesting, both for from the machine learning side as well as from the cryptography side.
Right. So explainability is a big issue. You want to say something, Stefan? No.
I fully agree. I do think explainability is, or should be, even much more important than currently is for our community, because it boils down to the question, why also do we do work what we do? Why do we do side channel attack with machine learning? Do we just do it so that we say, well, look, we broke something, which is nice to sell a paper or something, but in the end, you need to go back to a designer of the algorithm and say, well, there is a problem. And then the designer will ask, okay, but what is exactly the problem? And then with deep learning, machine learning approaches, you get in a situation where you say, well, I don't know, but I broke it. And the question then what we need to answer is how to improve the security. And to improve the security, we need to understand why deep learning broke something. And we need explainability for that. The question that for me is very interesting there is, this explainability is a very difficult problem in general. There is no good solutions. Would making explainability for crypto be simpler problem because we are somehow saying we use smaller neural networks, or will it be even more difficult because we are in a very niche setup where there is not a lot of people really interested in doing explainability for side channel or for neural distinguishers. So I hope it's easier, but I'm not sure it's an easier problem.
Wow, that's very, very fascinating. Fatema, any comment, any further comment about it?
Yeah, actually, it's a very interesting topic in general, not only for crypto, but explainability is useful. We know it is useful, but it boils down to asking the right question. And then I have been doing these type of approaches, and what I have observed is that you have collected some data set. Now you need to provide labels. What's the right label? What should I ask about this implementation? Should I ask that if the second round of A is working bad, or is it about the SWOT that is not working? Is it about the order that is not right? What question should I ask? Still, of course, with all the knowledge that we have in our field about A, yes. it has been a while that we have been working on AS, still making good questions and asking good questions to help us provide an explainable framework would be very difficult. I don't think it's impossible, but it is difficult. It's a difficult problem to tackle.
Yes.
Yes. So with the explainability question, I also think it is it's not only a matter of I mean, if one finds out, for instance, that one can break that a certain side channel attack works, if you use a neural network to extract some bit of the cipher state, then in some sense, on the one hand, you have a phenomenon that you don't understand because you don't understand how this extraction works, or you don't understand how a neural distinguisher works in detail. But on the other hand, you are just seeing a phenomenon that would have been there anyway. I mean, before you had that attack, you didn't understand that there was an attack to be found. So in that sense, I think these tools are sort of in a sense quite analogous, in my opinion, to observational tools that you use in other sciences. Let's say, I mean, you can't see a faraway galaxy, maybe, except if you use a telescope, but the telescope doesn't explain to you what you see. You make some observation, and then you have to explain it. That's always an additional work item that one has to do. So in that sense, I think the problem of explainability is not, it's slightly different than in other applications of AI, because in other applications of AI, one might have already a working process to solve some problem. We know that it can be done. And now we have a machine learning solution that can also do it. And we then want to, whereas here one sometimes finds things that one didn't expect to work, and they work, and that's a new phenomenon that one, just an observational phenomenon that one then has to explain.
Right, thank you. So we have two questions from the audience. So can you please, just a second.
Thanks. I'm just curious, are there concrete examples where a machine learning attack has then led to a well-understood algorithmic attack? And particularly for Kristen, do you think that your salsa attack suggests any special structure to the sparse LWE instances that you're solving that maybe could be turned into an algorithm, that a more well-understood algorithm?
Yeah, that's a very good question. I'm sorry, I can't answer it on the fly. There actually are some things that we're in the middle of working on, so I can't really talk about them. But I like the way you framed the question. Just, when we talk about explainability, I mean, another way of saying that is that can you look at what is happening inside the machine, in the machine learning and figure out what that attack is, and then just say what the attack is without training a big model. And like I said, these are not big models actually, so it should be a little bit easier, but I'm afraid I don't have a good answer for you yet, but I do like the framing of the question. I think that's a good way to think about what we should be trying to do.
So as an additional answer for instance, for my 2019 attack against reduced round spec, I think one has found out quite a few things, quite a few structural properties of specs that makes these neural networks work. So one can identify some smaller equivalence classes than these ciphertexts of specs. They can be grouped into equivalence classes of size 2 to the 16, and these have a very clear mathematical reason that they are there, and that they are smaller than the difference equivalence classes, and one can see that this is exactly the information that the network uses, because if you look at what the network outputs on one of these equivalence classes, then the output is constant, And so from that, when one observes this, one can then ask the question, why does it do that? And once one starts thinking about why does it do that, then there is a natural mathematical explanation for that. And I think in general, if one finds some attack that even I think if one finds in a cryptoanalytic attack that does something that is unexpected, then I think once one knows that the attack is there, that also even if neural networks were totally black box, which they aren't, because you can do a lot of things that you can't do with a black box. You can, for instance, retrain a neural network to do a slightly different task, and that's something that you can't do with a black box. Or you can look at the exact, you can look at how the network reacts to some. You can look at the exact probabilities that your network outputs. Okay, that you could do with a black box if the black box gives you probabilities and not just yes, no decisions. But you can also look at the weights, or you can delete some connections in the network and see what happens. So there are lots of experiments that you can do that you can't do with a black box and that you can do with a neural distinguisher, for instance. So in that sense, but even if it was just a complete black box, I think just the existence of some attack would motivate people to find out an explanation for that attack. That explanation would then usually not be identical, I think, to the actual mechanisms that the neural network uses. And I think, for instance, with the attempts to reverse engineer the attacks against spec, I mean, there has been especially one paper at Eurocrypt 21 that has looked at that has tried to get equivalent attacks with more traditional methods, and it's a very nice paper. But they certainly the mechanisms they use, they are things that the neural net wouldn't be able to do, because they rely on much larger lookup tables, whereas the network is quite small. It has a few 100,000 weights, and then this classical attack has on the order of a few tens of millions of weights that you have to learn. But it shows that you can find a classical explanation, which tells you which is something you've learned. So I think even a completely black box attack would lead to some classical explanation, maybe different from what the neural net actually does, but something that is still useful.
Thank you. Okay, let's move to another question. Yes.
Yeah, I think my question is quite related in part, because I was thinking more from the stream cipher or block cipher, that you do design them to not be reversible. So there's no learning through the algorithm per se. So these techniques is about learning the implementation of this. So it's going around the cipher and learning how you use it, implementing, how you fill in the keys, how you fill in the text. So I can see that there's a difference from that perspective, but Christine kind of took my idea there on the lattice base. Are you really going through the algorithm? I'm almost thinking like the Xbox is not reversible. So that's kind of tattoo in my mind. The Xbox is not reversible, so I should not learn an Xbox by trying. So I'm learning something else. At least on the lattice side, I'm thinking whether it's kind of similar that we're going around it and learning the implementation. So side channels being implementation stuff. So it looks like a language model to me, or it's really learning the internals of my choosing of the secrets or my biases. And I may have some question for you out of band because of this, because it seems quite interesting.
I could at least address part of that. Yes, so in fact, the model really is learning the secret. In fact, once we've trained the model, we have a lot of different methods to use it as a distinguisher to actually recover the secret. But you don't even need to recover the secret. Once you've trained the model takes an A, a random vector, and outputs basically roughly B. B is supposed to be the dot product with the secret plus some error. And that's enough to break encryption. You don't, it's just, it's an oracle now you can just use for decrypting things. You don't even need to find the secret actually, once it's actually, if it is trained well so that it's really high accuracy. I think the difference is in our case, I'm not sure if this is the point that you were asking about, we can actually recover the secret before it is trained to high accuracy. So it doesn't even have, to, if it's trained to high accuracy, then it can just decrypt things. The model can directly decrypt things. But we can recover secrets from it using our distinguishers without it being trained to high accuracy. So I don't know if there's an analog in the other.
So part of the question there was, if another lab implemented, would they learn the other labs? This lab knows its implementation because figure out that was a program that he learned versus the key that he learned, or is independent of implementation per se.
The LWE, it's independent of implementation. So.
Yeah, also for the symmetric cryptanalysis works, that's all completely independent of implementation. There's no I mean, in symmetric cryptanalysis, people have not been successful in directly recovering secrets so far. I think that's something that should be doable at some point, somehow, to some extent. For round-reduced ciphers, certainly. I mean, not full round is a different thing. But so far, I mean, for neurocryptanalysis of symmetric primitives, people have been getting distinguishers, and these distinguishers can then be used to recover a secret. But it's all completely on the logical level. There's no implementation knowledge in those impacts.
Yeah, interesting. Yes, Fatima, please.
What I would like to do is sharing what I have learned from great work published by Rivest and Goldrush. They know crypto very well, and they understand machine learning, theoretical machine learning. What they have said is that a good crypto should not be learnable. So algorithmic level, if we talk about crypto, it shouldn't be possible to attack it. We cannot learn the algorithm itself. Sparks should be irreversible. However, when you implement it, there are some shortcomings coming with the physical implementation of the thing, physical in the sense of software or hardware, and the limitations help the attacker to extract the secret, for instance, as we're discussing the LWE problem. By itself, it should be fine, no problem with the learning. But when you implement it, then you open the door to many different types of attacks.
Thank you. Okay. Okay, I don't know if I have another question for Christine. Christine, you are a very famous mathematician, and when you work in this area, you need to accept uncertainties that, as Stefan was mentioning before, certainly you may break something without basically knowing what's going on, or at certain extent. My question is kind of maybe to have your personal view, how a mathematician who has been trained to be formal, to have definition, theorems, etc., needs to adapt to this area. I don't know if you can share some of your thoughts.
Yeah, actually, thanks for the question. I wasn't planning on talking about this topic here, but it's just a question, opportunity for me to reflect on my career, because I started out as a number theorist and algebraic geometer. And so the first big transition was transitioning into cryptography, basically in 1999. So in cryptography, the main thing you have to get used to is that everything is big. Like, you know, I've had very, 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 very famous mathematicians ask me why crypto problems like pairing-based crypto, like why is that hard? Because they're thinking of an alphabet that has like 20 elements in it or something. And they're like, oh, why can't you just figure out which pairs with which thing, you know? So just that transition first for crypto to very, very large alphabets, like scaling up. So that transition requires you to switch over to this kind of algorithmic perspective where you're trying to quantify resources, like how much time does it take? How much space does it take? What are the steps in an algorithm rather than just an existence proof, like where a number theorist would just be happy with a theorem that says like a solution exists. They have no interest in actually finding the solution. So that was a huge transition. But then from crypto to AI is kind of interesting. It's like, it's another transition. Because as you said, we have these algorithms. I think of machine learning. Machine learning is algorithms, but they're just less well understood than a lot of mathematical algorithms. So I think what's happened and what's really amazingly cool, especially in the last, I'd say 10 years. So like Facebook AI research was started 10 years ago, is that those communities really started thinking about, okay, well, how do we build the community and the tools to make AI successful rather than just being something that exists in a bunch of papers? And so they really thought about, okay, how do we build the data sets so that all our new algorithms can be tested consistently on these benchmark data sets? And so a lot of people just put a lot of work into building data sets and then building the machine, like PyTorch is the big thing that FAIR has contributed. And there's startup companies all around the world that are building their commercial products on PyTorch, which is just a released set of ML algorithms, with based on neural nets and other things. So making these algorithms efficient, making them usable, and then putting the work into building the communities around benchmarking using all this stuff. And so then the result is that these tools are out there useful for PhD students. So PhD students actually can just show up and start using these tools without having any of the mathematical coursework to know what these algorithms are underneath. And so I think that's like a huge transition now that we've seen in the community is that we have thousands of people using these tools without knowing the mathematics of the algorithms underneath. And so I actually think that's a really important opportunity for more mathematicians to work on these algorithms and to understand things better. But I'm not sure if I really answered your question, but at least you get a flavor of my experience anyway with the communities.
Yes, thank you very much. Any further comments? Okay, Aaron, I have a question for you. These AI-assisted side channel analysis, in your experience, are already being applied outside of the academic realm and in the industry?
I mean, there's certainly AI-based side channel analysis is being used in other contexts. Yeah, certainly. I mean, it's AI-based side channel analysis is, by now, I would say, more or less, it's a standard approach to doing side channels, I would say. And so, of course, it's used by people who are trying to certify things.
Thank you very much. Yes, please.
Yes, as far as I know, indeed, it's used by many, many companies. What I do hear when talking with people from companies is that they do struggle quite a bit more to get the levels of success reported by academia. So we in academia all commonly say, well, we break something, it was crazy easy. And then when we talk with people from industry, they say, oh, we kind of broke it, but it was not easy. They kind of need mostly much more bigger data sets, bigger models, more tuning. So there does seem to be quite a gap between academia and industry, but it is used and it should be used much more by industry. But I think this gap is a problem because, like I said, we in academia report relatively easy paths towards success. Does not seem so easy in industry.
Okay, interesting. Yeah. Also another question for Aaron. In this machine learning cryptanalysis, people has focused mainly in neural distinguishers. Are there any other ways in which AI could plausibly be used for cryptanalysis in the relatively near future, not like too far away?
Yeah, I think certainly one could see it certainly. I think there are a couple of different things that one could do with AI in cryptanalysis. So, for instance, one thing that people have been doing relatively little research on is key recovery mechanisms, because I mean, for instance, all of the especially the neural cryptanalysis attacks, they of course they use distinguishers that have very high performance, but they have in terms of how well they distinguish the ciphertext from random, but they are also fairly heavy compared to tests that you would normally do in symmetric cryptography. And therefore, in order for all of this to work, you have to develop very efficient key search policies. And the mainstay of, or the main strategy that is being used is still more or less in most papers the one that was established in my Crypto 2019 paper, which is based on Bayesian, on a kind of a Bayesian optimization applied to key search, which is of course an AI-inspired technique. But I think that there is probably a whole zoo of highly selective key search policies that one could find if one working with. And I think for that kind of thing, AI could be quite useful. I think also that in the not too distant future, I think that it's conceivable that classical algorithms could be discovered by AI, sort of like this using techniques similar to the recent DeepMind papers that looked at matrix multiplication algorithms. And lastly, and I think that might be something that a lot of people will very strongly doubt, is that I think that maybe within a few years one could also imagine large language models doing interesting cryptanalysis. If they are, what I could imagine sort of is that you have a large language model, you give it some cryptanalytic tools, so you give it sort of a toolbox to work with, you explain to it the tools and how to use them, and then set it to try to give you some first idea of how to cryptanalyze a primitive, and then you would get sort of as an output first approximation to a report about what the security margins are and what the best trails are and so on. And I think current models like GPT-4, they are not quite up to it in terms of reasoning capability, but I don't think they are infinitely far away from being able to do that kind of work.
Yes, please.
I know it's near the end of the panel, so good point to bring up some controversial issue. It's just something you said made me think of it as I think it leads well into the next panel too on the privacy preserving. I think so. When we think about preserving privacy with crypto tools, so like I said, one of the things I had worked on for a long time was homomorphic encryption to protect privacy of data in the AI pipeline. So if you have everything encrypted, like all the data is encrypted and when you're training, and then you do encrypted inference, it's a lot harder for an adversary to get in there and start, modifying things because they're not able to see, what you're doing. I mean, I know you have to analyze that statement a little bit more fine-grained, but so, I actually had people accuse me, when I was working at Microsoft, that we were trying to propose homomorphic encryption as a way to basically hide everything we were doing and do malicious stuff, like as assuming kind of malicious intent, which is not a really very good assumption. It's like in the previous panel, people were saying that, big tech has every incentive to do everything above board. And so there's no real reason to assume a malicious intent. But the interesting thing for me is if you look at the whole field of adversarial ML and you look at people that are actually going under the covers in the ML algorithms to, adjust things either to prevent attacks or to make attacks, I think crypto is something that can actually help to preserve, the workflow and make it less disruptable by adversaries. But then there's this controversy as to whether we're, like trying to lock everything down and do something like, untoward under the covers. So I just think this is a kind of an interesting controversial topic for discussion. I don't know if it'll come up later, but that crypto can work hand in hand with AI, but there are ways in which people will certainly perceive it differently.
Differently.
Mhm.
Yeah. Any comment? Any further comment about it? Okay, I have one final question, maybe for Stefan. Stefan, do you think that at one point in the distant future, maybe we can have these AI-based side channel attacks that they become fully autonomous without the intervention of humans?
One distant enough for sure. Yeah, it's difficult question. I mean, realistically speaking, even many things most of the things done up to today is done with AES, and then even going from AES to some other symmetric algorithm often is far from trivial. And then, going to public key crypto, there is a gap. Then going to post-quantum, there is a much bigger gap. And then now thinking something that is automated, I mean, it also depends on what level. If you just talk about fine-tuning or hyperparameter tuning, yes, we can use Bayesian optimization or this and that, and then we do search, sure. But I do feel for many, many, many years, human expertise will remain extremely important part. And then, who knows?
Yeah, because in the other table, I think Matt was saying that what are the most scariest things that we can expect from AI? So you wouldn't count that they will be fully autonomous in this kind of attacks. So it's one of in the list.
But I mean, considering that AI-based side channel is, let's say, active for 10, 12 years now, and deep learning from 2016, so 7-ish years. Considering the level of progress we have up to now, it's hard to expect very soon that we will have fully out. But considering how fast AI develops, who knows, next year maybe some GPT-24 model will work so nicely that all the problems will be solved.
Okay. I mean, yes, please.
I mean, what is missing, I think, what is really sorely missing for a fully automated side channel analysis pipeline is simply the reasoning ability, because there is if you design a side channel attack, then there is you can broadly break it down into a workflow where you have to figure out what you have a certain primitives that you want to attack, and then you need to look at what are the secrets that I would like to extract, because there can be several types of secrets in the primitives that are potentially valuable. There can be several points where you might find something that allows you to derive the keys. And then, and you need to figure out which ones are the ones that are promising in terms of extracting them. And of course, that has to take into account the countermeasures that may be present in an implementation. And then you have to try to extract them. And I think AI is at the moment quite good at once you have fixed all the hyperparameters and so on, at the try to extract part, because you can gather a large data set and you can easily label it. You can in fact much more easily label it than for most other applications of AI, because you have the actual ground truth is, you know the key, you know what's happening. When you have a masked implementation, you may even know the masking secrets, because you can make the implementation spit them out. So you know the ground truth. And at that part, AI is quite good, but the reasoning ability that is missing. And in terms of getting there, in terms of getting that reasoning ability, the only plausible pathway that is visible in contemporary, in current technology is large language models, probably with given some tool set, given some explanations, and maybe also given some extension like tree search. I mean, because searching over a space of possibilities, doing search, that is something that frequently allows you to find much more complex solutions to a problem. I mean, for instance, one can see that very, very easily in other domains where AI is very good. Let's take, for instance, chess. We have chess programs that are very, very good, that are much better than humans, but they look at a large search tree of possible moves and counter moves and so on. And I find it quite interesting in that regard that if you let a neural network play chess, just the pure neural network, it will play the best ones will play about master level. But if you then attach a relatively small key search, you can get to superhuman level quite with a very modest amount of search. And we don't have the search component yet really in large language models, because we don't know how to verify and how. But in that sense, I think it's very hard to make a prediction that definitively says one cannot have a fully automated workflow in, I don't know, 5 or 10 years.
Nice example. Thank you very much. So I'm using a bit of the audience. I will ask each one of our panelists to briefly just summarize what will be your message to the audience from this table discussion. I don't know who wants to start. Maybe Christine?
I can start and be very brief. Just the idea that AI models, which are really just mathematical models, can be trained to learn things, to attack crypto. And that ranges from what you've heard on the side channel type of attacks to actually attacking crypto primitives to some extent, at least. And I just think that's a really interesting point that we're at in the world right now, that we can actually use AI to attack crypto systems.
Thank you, Christine. Fatima?
What would they say? The take-home message is, let's talk. Let's talk about not only cryptanalysis, but also let's talk with other colleagues from other domains and see what they have learned so far. Crypto and AI are meant to be together. They can be seen as two sides of the same coin. This is not my argument, but I can quote from Rivers. If we talk, perhaps we can find better solutions to the problems that we have been discussing today.
Thank you very much, Fatima. Aaron?
Yes, so I think both AI-based cryptanalysis and AI-based side channel analysis, they are fascinating fields that do sometimes surprising things, because it is surprising that you can, at least to me, it is surprising a priori that you can look, for instance, at a power trace and read out an AES key. It's not something that one would expect if one hadn't
Like magic.
And it's also, I think research in AI-based cryptanalysis can also tell us something about the capabilities of small neural networks, because it is, for instance, a surprising capability that one can use a small neural network to basically to recover the key of a block cipher. And I think in these areas, one will see a lot of, there will be, I think, a lot of new developments in the next few years.
Thank you very much, Aaron. Stefan?
I will connect with explainability, because that's something we discussed a lot. So I feel that's a big part of our effort where we need to go. But also it's very important to understand better what do we even mean when we say explainability. So what is explainability? What kind of questions do we want to answer? So that's also a message for the audience. Just also think what is explainability for AI-assisted side channel, or what kind of questions? Why, when, so what? There are so many questions. Not all questions are equally easily or difficult to answer. So we should understand also what kind of questions can and we should answer.
Okay, and with that, we conclude the table, so please. round of applause. Thank you very much. So we are ready for lunch and see you later.